testing week. So that means tomorrow, all of the seniors will be doing work keys, which will be up here at BHS. All seniors here for virtual are coming to BHS tomorrow. So you'll have room assignments, all that good stuff. Juniors get to stay home. So juniors get a day when they don't have to be at school and everyone else does, because freshmen and sophomores have to come to the high schools also because they have ACT Aspire testing. But you guys are past that. So you will have juniors, and there's just a couple of juniors in here. You get to stay home and work on your stuff, whatever you're working on there, while oops, I hit something I wanted there. While the seniors come up here and hang out with me. Well, not all of you. Some of you will be hanging out with me, but not the whole group. So we're splitting a couple of us teachers that will be handling the work keys testing, but we'll be done before lunchtime. So you'll get to leave early. Unlike all these folks down the hallway in the classrooms, they have to stay the whole day, even after testing. So all right, let me get this set up for us to look at our lesson this week. Our lessons, we have 2 lessons this week. We're starting our new unit, so we pull it up here. So Algebra 3. Say I got a new class in here in my student app there, but a class I'm considering teaching next year, so we may add to our programming classes. Algebra 3. Let's go to our grade screen. All right. We are finally through with matrices. The last quiz was due last night, Sunday night here, April 16th. So we are through with that, and we are starting our last module, rational functions. Hopefully this will be a little bit easier finish than the matrices. We're going to start with quadratics. I know you guys are very familiar with quadratic functions. You've been working with those for years. We're going to talk about polynomial functions of a higher degree, real zeros, complex zeros, the fundamental theorem of algebra, and finish up with rational functions and graphing of rational functions and their asymptotes. And then I have the semester final already loaded in, which for all you seniors is not going to be May 26th. It is like the 10th and 11th or whatever that Monday and Tuesday is after your last week of school. So hopefully you're exempt or will be exempt because it's not finalized yet. Remember, you got to have 4 or fewer absences and or tardies in whatever class you want to be exempt from. 4 or fewer absences or tardies in your advisory class. And you have to have a grade of 75% or higher in the class you want to exempt. And you cannot have any missing assignments. So if you've missed any of these matrices assignments, and that's all that's keeping you from being exempt, I'd go get these done. So there was quite a few assignments in there. They don't take very long. But if you're missing any of them, you will not be exempt from the final. So, all right. Let's look at our lessons this week. Module 8, quadratic functions. Quadratic functions. And again, this is a good starting place for this unit because you guys have worked quadratic functions for years. This is one of those lessons that's just all on one page. You know, it's got everything. The first part up here, the scenic overlook, that's what we're going to go through. That just summarizes. So the scenic overlook summarizes, and then this is the actual start of the lesson in more detail with more examples. So we'll look at the summary up here that's in the blue part, the scenic overlook. So first, let's start with just a definition of a polynomial function. What is a polynomial function? Well, we let n be a non-negative integer and let a sub n be real numbers with a sub n not equal to 0. So a function is defined as a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power. So a is just the first coefficient. First coefficient can't be 0 or else you don't have any term there. And x to the n means if it's a 4th degree, if n is 4, then you've got a coefficient for the 4th term and x to the 4th. And then you'd have the coefficient for the 3rd term with x to the 3rd plus the coefficient for the 1st, all the way down to where you just have the constant a sub 0. Right? So that's just the technical mathematical definition. Don't let that freak you out. It's just the same stuff you've been working with all through high school. Generally, we write the polynomial in descending order with the highest degree term first. So we would start with like x to the fourth, and then go x to the third, and x to the second, go in order, going down when we write those. And we classify them by degree, right? It's a third degree, it's a second degree, it's a fourth degree, whatever. All right, we're going to study polynomials starting out with a degree of 2 called quadratic functions. Nothing new there. Definition of a quadratic function. Let a, b, and c be real numbers with a not equal to 0. If a is equal to 0, we don't have a quadratic function because our x squared term does not exist. So that's the only rule here. So f of x equals ax squared plus bx plus c. That's a quadratic function as long as we have a. Right, the graph is a U-shaped curve called a parabola. They're symmetric around a line called the axis of symmetry. Right, that's the mirror line down the middle of it. The point where it intersects the axis is called the vertex, the axis of the axis of symmetry. Wherever it intersects that would be the vertex. That'd be either the highest or lowest point, or if it's a sideways one, it would be a minimum or maximum in the x value. A parabola opens upward if the leading coefficient's positive, and downward if the leading coefficient's negative. If that a is a negative number, it's a downward pointing parabola. The simplest quadratic function is just ax squared, especially with a equals 1. It'd just be f of x equals x squared. In this case, it has a vertex of 0, 0. The axis of symmetry is the y-axis. The parabola opens upward when a is greater than 0, downward when it's less than 0. So let's look at the text and see the shape and visualize it there. So if we looked at these functions, how would it differ from just ax squared? If we have 1/4 x squared, it's going to be wider. Let's look at just a few of those. We'll pull up our little graphing calculator. They do +4, they do a 4, a -4. All right, so let's play around just a little bit with it. F of x equals x squared. That's the standard parabola. We're very familiar with the standard parabola. If it's 1/4 x squared, wider. So I'm going to leave the original one up here, equals x squared. There's the original. The blue one is the original. But if we do 1/4 x squared, it's wider. It's compressed basically downward. It's squished a little bit. If we just make that 1/4 a 4, now it's skinnier. It's skinnier because it's going up faster. Whatever the y was here, now it's multiplied by 4. So it's a lot higher up there than it used to be when it's down here. This x here that's at 1 jumps up here to 4, right? So let me change this real quick. I don't like it does the halves. There we go. Let's do it by the ones. So yeah, from 1 goes to 4, everything's higher. If we do -2, it just moves it down. It's the same shape, it just moves it down. If we do a +3, it just moves it up. Right, so we can manipulate our original quadratic in lots of ways, which we know about transformations and all that good stuff. Oh, we didn't do a negative. If we make it if we made it a 4, it was that. But if it's a -4, it just goes downward, opens downward instead of upward. All right. Now the vertex form. If you have a quadratic equation, it could be written this way: f of x equals a to the x minus h squared plus k. A x minus h squared plus k. Let's write one like that over here. A will be 2 x minus h. We're going to do our h is 3 squared and then plus k. So we'll say plus 2. So this is a quadratic. We see that by the parabola. And the h and the k are 3 and 2. Well, let's look at that point 3, 2. That is the vertex based on our h and k. If we make our k a negative, let's say it's -2, that just moves our vertex down to -2. If we make the h negative, let's say we wanted to make it a -3. So if we said x minus a -3, right, that moves the vertex over here. We wouldn't say minus a negative because when you minus a negative, that's the same thing as plus. But notice the vertex doesn't move. X minus -3 is the same thing as x plus 3. So that is our vertex. So this vertex form is called the vertex form because right there in the equation, we can see what the vertex is. based on the h and the k. If we take off the 2, it just changes how wide it is. It doesn't change the vertex. H and k are the important parts of the vertex form. So here's where they take a regular equation, 5x squared plus 10x plus 6, and they use completing the square methodology to convert it to the vertex form. So we can see the vertex is at -1 and 1, because x minus -1 would be the h and 1, so -1, 1. We couldn't tell from this 5x squared plus 10x plus 6, that doesn't tell us what the vertex is. But when we change it to vertex form, we can do that. So it wants us to put the standard quadratic into vertex form. So let's practice one of those together, just because I know it's been a while since you've been completing the square. So let me put this up here. All right, let me write down what that problem was first. F of x equals, I'm going to do the second one, x squared plus 6x plus 2. Oh, minus 2. Minus 2. All right, so now we'll bring this back up. All right, when we're completing the square, we have, in this case, with no coefficient out front, we want to make this a perfect square to where we can factor it into two binomials that are identical. So to do that, we take whatever the x term is, which is 6, and we divide that in half. So you got a 3. And then whatever that is, you square it. So we're going to add a 9. So this becomes x squared plus 6x plus 9. But we've changed the equation when we added 9, so we also have to subtract 9. So now it's still the same equation now, because I added 9 and subtract 9. So that way it's still the same. If I don't subtract the 9, I change it. It's not the same quadratic equation any longer. But you take that middle term, take that middle term, the 6, divide it in half, and then square it. Right? Divide it in half and then square it. And that gives you the term that goes here. So now this factors to x plus 3, x plus 3 minus 11. Right? Because we made this a perfect square trinomial by doing this process. So when you multiply those back together, you get this. So this is f of x equals x plus 3 squared minus 11. So our h is -3 and our k is -11. So that tells us the vertex. We convert to vertex form. So let's check our work. We've done that. Let's go to Desmos, graph this equation. The original equation was x squared plus 6x minus 2. And we said on ours that's -3, -11. Let's see. Oh, there it is, -3, -11. So we obviously factored it correctly because that is where the vertex ended up. So in vertex form, we know that it is -3, -11. So it's x plus 3 squared minus 11 is the vertex form by completing the square. The only thing to watch out for, I'm just going to change this real quick just to warn you about something. If this was 2x squared plus 6x minus 2, and we factored out a 2 at the beginning, just to make that simpler, x squared plus 3x minus 1. Now this example doesn't work well. Let's make this an 8 because we're going to work with fractions. We don't want to work with fractions. So that makes that a 4x. So if we're going to make this a perfect square, 2, and we say x squared plus 4x, we take 4 divided by 2 is 2, 2 squared is 4, so we add 4, and then we get the minus 1 out here. We also have to subtract the 4, but in this case, since we factored out, this isn't 4 really, it's 2 times 4, so we would have to multiply 2 to anything we bring outside that parentheses. We would subtract 8 in that case because there's a 2 times the 4. So if we're going to, because you could also write it that you're putting it inside. If you do plus 4 minus 4 parentheses, it doesn't matter what order I write that, plus 4 minus 4. When I bring that minus 4 outside, it's being multiplied by 2. So it becomes a minus 8 out here. So this would factor to 2 times x plus 2 squared minus 9. So just remember, if you factor something out first, when you pull that out of the parentheses, don't forget to multiply it by whatever you factor it by. All right, just a little heads up there, because that's where we get the wrong answer. We're like, what? So like on this one, if you factored out a 3, and if you group this and then factored the 3 out of it, you'd have to do that. Here's the check your answers, by the way. So if you work those two, you can check your answers right here. Click on that. It'll take you to this other document that has the answers. There it is. It loads slowly. But see, they factored the 3 out, and they added a 4, so they had to subtract a 12 and that there. So that's what they're doing, if you're wondering. All right. You solve a quadratic equation by setting it equal to 0, right? So that'll tell us what the factors are, what the zeros are. X squared plus 3x plus 2 equals 0 would factor to x plus 2, x minus 1 equals 0. So if x plus 2 equals 0, x is negative 2. If x plus 1 equals 0, it's negative 1. So those are called the zeros, or the factor, the zeros are the solutions for this function right here. If the quadratic's not factorable, or if it's hard to find it, you can always use the quadratic formula, right? And here's the quadratic formula right here. You notice this is a link, because I've given you a little fun video right there. If we click on that link, it'll open up my quadratic formula video, which some of you may be wondering in my video opening where all that comes from, because I got this video I made about 3 years ago. Let's see. That's a nice goofy look on my face too. I stopped at the perfect place. So there you go. Fun little video that I have linked into our lesson right here that you can go see. Quadratic formula. It's just a couple of minutes. It's just kind of fun. But it's a story that my professor told me 35 years ago. But yeah, you can use the quadratic formula and it'll find the solutions, like 5 plus or minus the square root of 17 over 4. That's not a nice factorable quadratic. So, all right, that is more detail down here. If you want to go through this, that'd be great to do. And it gives you more examples of what we just talked about. The vertex form goes through the quadratic formula, finding the vertex and axis of symmetry. And so characterizing the nature of a quadratic function, the polynomial degree 2. Here's what it looks algebraically in either form, vertex or standard. When you graph it, the parabola has a vertex at hk. It opens upward if a is greater than 0, downward. So there's a nice summary for quadratics right here. The initial value, the y-intercept, is where f of 0 is. When you put a 0 in there, that'll give you the y-intercept, which is the c. And then there, the x-intercepts you can find with the quadratic formula. So, all right, let's look at the second lesson. We can look at the first assignment. It's just a quiz. It's got 1, 2, 3, 4, 5. Let me talk about this fifth one real quick. A projectile thrown upward, so the distance above ground after t seconds is given by this function. So this is a quadratic formula. It just uses t instead of x. After how many seconds does the projectile take to reach its maximum height? Oh, okay. So if we had a formula, let's just make one up. Negative 16 x. I'm going to change it to x for graphing purposes. Plus 12x. Oh, 16. If we look at this, I probably need to make that different. Let's see. I want it to be a bigger number, so let's make it 112. 112. All right, so if we had this formula and wants to know this projectile takes off, how long to reach its maximum height? Well, that would be the vertex, right? Where does this graph hit its maximum? Well, this one goes way up there because I put a big number in. So the maximum height would be the y value at the vertex. Let's get to the vertex. The maximum height is 212. That is the height. But the question was, how many seconds does it take to get there? So I have to find the vertex. So if I have it in vertex form, this is easy. It takes 3.5 seconds because at 3.5, the value is 212. So I'm just trying to find the vertex of the equation. And then from the vertex, I know at 3.5 seconds, it's 212 feet high or whatever, meters high or whatever they're using in the problem. But the vertex tells you everything you need to know, the amount of time and the height. So just look and see what they're asking for. Like in this one, how many seconds? So this is looking at the x, right? So you got to show your work, use this equation, convert it to vertex form, and it'll tell you right there. All right, let's move on to the next lesson here. I want to keep you all day. Come on, here we go. Now we're looking at polynomial functions of a higher degree. So we looked at x squared. Now let's look at x is bigger than second degree. So we know degree of 0, 1, and 2. We know how to draw those. But greater than 2 is sometimes a little more difficult. So let's look at general features of polynomial graphs. They're continuous. If you have a polynomial, it's continuous. There's no break in the graph. It's one continuous line. You can draw the graph without lifting your pencil because you can just continue on. There's no sharp or pointed turns in a polynomial. Not like absolute value that's actually a V pointed with a point. These are smooth and rounded. And the easiest ones to see are just in the form of f of x equals x to the n, where n is some number that's greater than 0. X to the third, x to the fifth, x to the sixth, whatever it is. If n is even, it makes a U shape and touches the axis at 0, 0. If there's no other things, if it's just like x to the fourth, x to the 10th. If it's odd, it has an S shape. So let's look at some of these. X to the third, x to the fourth. All right. So if we did, and I need to get back way back down where our axis is. There we go. All right. Now we'll zoom in here so we can kind of see what we're talking about. All right. So if we have f of x equals x to the fourth. So yeah, if it's a U shape, it's kind of flatter than a parabola. If it was just x squared, you know, it's different than fourth. If we do sixth, it gets even flatter at the bottom. 10th, well, we do that. But if we do an odd number like the third, oops, it went sub 3. Third, it's like an S shape kind of. If we do the fifth, it just gets flatter again. If we do 13th, do 19th, it almost turns into, it's almost a corner, but it is curved. If you zoom in, it does curve. It doesn't sharpen, but that's just the bigger you go on that. Oh, that's 119th. No wonder it looks so flat. There's 19th. But odd numbers take like an S and they'll cross over. Even numbers, 20. Oh, it keeps doing that. 20 are like a parabola, but they get flatter and flatter the bigger the exponent is. So, all right, let's talk about the binomial theorem and Pascal's triangle. The binomial theorem takes some work, and it's talking about expanding a binomial. So if you have a plus b to the 0, that's just equals to 1. That was an easy one. A plus b to the first is just a plus b. But when you start getting bigger, a plus b squared, which would be a plus b times a plus b, that's a squared plus 2ab plus b. A plus b to the third, now you've got more work. You've got a plus b, and you have to multiply that by a squared plus 2ab plus b squared, and it just gets bigger and bigger. So we can kind of look at one of those with some real numbers. Let's write down, let's say, just for example, I'm going to put the a plus b example here, and I'm going to say it's to the third power, which would be a plus b to the a squared plus 2ab plus b squared, which is the same thing as a to the third power, which is a to the third plus 3a squared b plus 3ab squared plus b to the third. All right, now I've got that copied down. I'm going to put it up here on the screen. So the binomial theorem says we can just multiply these out. And let's put in something for a and b. Let's put x, let's do x plus y to the third power. What does that equal? Well, that equals x plus y times x squared plus 2xy plus y squared, which equals, this tells us right here, it equals x to the third plus 3x squared y plus 3xy squared plus y to the third. Now, we didn't even have to do a lot of the math where we have to distribute, we have to distribute the x to all three terms, distribute the y. Binomial theorem already tells us what the coefficients are going to be. This coefficient is 1, this one's 3, this one's 3, this one's 1. And that continues on. But let me show you something even cooler. Is Pascal, he figured out a lot of stuff out. And he has what he calls Pascal's triangle. Now, let me go to check your answers. I'll show you how his triangle works. All right. It's going to pull it up here. Oh, this didn't show the triangle. This is checking your answers. Hold on. The triangle's down here. Must be farther. It's in the actual part of the program down here. All right. Where's his? Oh, did I totally skip it? Thought I had a link to it up here somewhere. Pascal's triangle. Oh, here it is, right here. I skipped it. There's a little blue right there. There's a link to Pascal's triangle. So his triangle says this. This is a plus b 0 through a plus b to the third. Here's this triangle. 1, 1, 1, 1, 2, 1, 1. So this is saying if I have a plus b, I'm going to write these down here. A plus b the first, a plus b the second, a plus b the third. Okay, so this says, now I got those written down. Okay, it says the coefficient for the 0 power is just 1 because the answer is actually 1. Because anything to the 0 power is 1. So it doesn't matter what a plus b is. This one says it's 1 and 1. These are the coefficients. So you take the first one. So it'd be 1a plus 1b, which is just a plus b, right? And then it says, if we expand this, 1, 1, and then these two add together to be 2. So it means a plus b squared would be 1a squared plus 2ab plus b squared. The coefficients are 1, 2, and 1. If we expand it even more, now we put another 1 out here. We add these two together, and that's 3. Add these two together, and that's 3. And then another 1. So that's saying the third power, this is to the third power. So our first term is going to be the third power, a to the third plus 3. No, we see it up here. The coefficients were 1, 3, 3, and 1. And each term, I'll move over here and let's do a to the fourth. So it'd be 1 plus we'd have to add those two together, which is 4, and add those two together, which is 6, and add those two together, which is 4, and then put another 1 on the end. So I know our first term would be to the fourth power, and it's just 1. So it'd be a to the fourth. Now the next one, we go a to the third, and a to the second, and a all the way down. And it would be a 4, a to the third, and now we've got to add the b. And then we have 6 a squared b squared. The b is getting bigger and the a is getting smaller. Plus another 4ab to the third, and then finally just 1b to the fourth. So if we had x minus 2, we could just substitute 2 and x in there and then solve it. Because 2 squared, 2 to the third, 2 to the fourth, we could write the whole thing across there, the -2. If we go to the fifth power, a plus b to the fifth, here's the coefficients. 1, 5, 10, that's 10, 10, 5, and 1. This will be the coefficients, starting with a to the fifth, and then 5a to the fourth b, plus 10a to the third b squared, plus 10a squared b to the third, plus 5ab to the fourth, plus b to the fifth. And Pascal's triangle just continues on and on and on, and you can grow. And as long as you know the one above it, you can add ones on both ends and then add these together. 6, 15, 20, 15, and 6. And that is the coefficient when you multiply two binomials together. It's a pretty cool little shortcut. And we can go on the internet here and say Pascal's triangle and find it for a long ways. Now look at there. See there, it keeps going all the way down. Row 4, row 5, row 6, row 7, row 8, and it'll give you the coefficients on and on and on and on. It's a pretty cool shortcut that Pascal created for us. So yeah, look at the fifth row. And here it works out the fifth row. A plus b to the fourth. That's the 0 power, first power, second power, third power, fourth power. So it starts with a to the fourth, goes down to a to the third, a to the second, a to the first. And it actually has b to the 0 in the first one, but b to the 0 is just 1. And the last term has a to the 0. So it actually does start at both ends and works its way back up and down. And then it just simplifies there because you get rid of it. So here's an example using x minus 3 to the fourth power, using the binomial theorem and Pascal's triangle. So here's the binomial theorem, spreading that out. But when you substitute the x minus 3 into it, the -3, you got to take it to the first power, and then you got to take it to the second power, then you got to take it to the third power, and you got to take it to the fourth power. So it ends up alternating negatives. But there's what it simplifies to, which is a lot easier than doing all that by hand, where you're multiplying x minus 3 times itself 4 times. That's a lot of distributing, a lot of writing. You're going to take half a page of paper doing that. But using Pascal's triangle, you can just fill in the gaps and then simplify it. So you filled it in there and simplified it. A lot faster than doing it all by hand. So pretty cool thing there, the binomial theorem and Pascal's triangle. Leading coefficient test. What is the first coefficient? Right? So we know with the leading coefficient, it's going to affect two things. If it's positive or negative, it affects which way the graph goes. If it's odd or even. So it tells us a lot because we talk a lot of times about the end behaviors. So let's go back to our graphs here. Let's go back to just a leading coefficient of 3x to the squared, right? So given that it's a positive number, we know it's going to go up. If that 3 was a negative number, it would say the graph is going down. And that works the same for every even, fourth power, sixth power, that both ends, when we talk about the end behavior, both ends go towards infinity or both ends go towards a negative infinity with the negative coefficient. However, if it is on an odd number function, let's say to the third power, if it's positive, that means the right end is going to infinity, but the left end is going to negative infinity. At the right end over here, as x gets bigger, as x approaches infinity, as x gets bigger and bigger, the function gets bigger and bigger. So it approaches infinity. But as x approaches negative infinity, as x is going this way, it's going to negative infinity. So the right end goes to infinity, the left end goes to negative infinity. But if we have a negative coefficient, it's a negative 3x, it's just the opposite. Now as x is going to infinity, the function is going to negative infinity, but as x is going to negative infinity, it's going to positive infinity. So that coefficient, the leading coefficient, tells you a lot about your graph. The degree of the graph tells you whether or not it's an S shape, whether the ends go different directions or the ends go the same direction. And the leading coefficient tells you which way those ends go. So you can get a visual image just looking at this. This is x to the fifth, and it has a coefficient of 1. So we know it's x to the fifth, that the right end is going to go to infinity. I guess that's the right end for you guys. And the left end is going to go to negative infinity. On this one's a negative x to the fifth. So that's just the opposite. The left end is going to go to infinity, and the right end is going to negative infinity. Doesn't matter if it's a fraction. Negative 3/2 x to the sixth. X to the sixth means both ends are going the same direction. And the fact that it's negative means that both ends are going down. It doesn't matter that there's this other 2/3 x over here. We're looking at the leading coefficient. Zeros of polynomial functions. That's, if we graph it, that's where it crosses the x-axis. If we factor it, that's where it equals to 0 at. When you set a polynomial function equal to 0, you can factor it and find the zeros. Right? So if there is a function of x to the n, it'll have n at most, n real zeros. The x to the fourth, it won't have more than 4 real zeros. In fact, it may have less. Maybe some of those zeros are imaginary. So these are all saying the same thing. X equals a is the zero of the function. We could also say x equals a is the solution for the polynomial when it's set equal to 0. We could say x minus a is a factor of the polynomial, or a comma 0 is the x-intercept. Those are all talking about the same points, same thing. So let's look at a real example here. 2x to the fifth. Let's do this. All right, if we graphed 2x to the fifth, 2x to the fifth, minus 6x to the fourth, plus 4x to the third. All right, so we have graphed that. It says the solutions are 0, 2, and 1. Well, let's see what they're talking about. The solutions are, there's 1, there's 1, there's 1. Those are the solutions. Also could say those are the zeros. We can also say that those are the x-intercepts. And from that, we know what the factors are. Because, I'll put this back over here.
615.75.
Yeah, there's x-intercepts, all that. See, the factors are, let's do one of those real quick, because you're going to have something like that on your assignment this week. What if we just know what the factors are? Can we figure out what the equation is? So if I put this back up here, and we know the factors, the solutions are x equals 2, negative 2, and let's say square root of 3 and negative square root of 3. So that tells us this must be at least a fourth degree polynomial, because there are 4 zeros or 4 solutions. Well, what are those? Can we write this function? Absolutely. Since we know that these are the zeros, that means when the x is 2, the function equals 0. So what would that factor be? Well, that factor would be when x minus 2 equals 0. Because x is 2. 2 minus 2 equals 0. All we have to do is take these factors and write their opposites. Negative 2 would be x plus 2. X minus the square root of 3. And x plus the square root of 3. Oh, I don't need this one then. So f of x equals x minus 2, x plus 2, x minus the square root of 3, x plus the square root of 3. That is the function that has these points, that has these zeros. And we can prove that by putting that right into Desmos. Let's write that function. X minus 2, x plus 2, where'd all the rest of this? X minus the square root of 3 and x plus the square root of 3. Square root of 3, it's about 1.7 something, right? There it is. So there are the 4 zeros. 2, negative 2. This is the rounded decimal equivalent of the square root of 3 and the negative square root of 3. So we wrote the function that had those 4 zeros that we were given to start with. So what happens when they want us to write that in standard form? Well, it takes a little bit of work, but we can do that. So if we want to write this in standard form, we would have to multiply it out. X times x is x squared. X times 2 is 2x. Negative 2 times x, and then negative 2 times 2. So the first one would simplify, because these cancel each other out. X squared minus 4. Then we can multiply these two terms together. X times x is x squared. X times the square root of 3, square root of 3x. Negative 3, so be minus the square root of 3x. X is not part. I probably should put the x first because it's not underneath there, and it kind of looks like it is. So plus x square roots of 3 and minus x square roots of 3. And then the square root of 3 times the negative square root of 3 is just minus 3 because the square roots cancel each other out. So this simplifies to x squared. These cancel each other out. X square root of 3 minus x square root of 3 is 0. So now we've got it down to this. We just have to multiply these times each other. So f of x equals x squared times x squared is x to the 4th. X squared times negative 3, negative 3x squared. Negative 4 times x squared, and negative 4 times negative 3. So that equals x to the 4th. These are like terms. They're both x squareds. So we have minus 7x squared plus 12. So that's the same thing. We can prove that we did that correctly. If we type in that new equation, it should be the exact same graph. It should be the exact same equation if we did that correctly. I love using graphing to test my work. Oh, there it is. Take away the black graph, there's the purple graph. It's the same graph. Take away the purple graph, put the black graph. Same graph. So if it's the same graph, it's the same equation. So we just tested our work right there. The intermediate value theorem. This is an interesting one. We don't talk about this very often. This says, let A and B be real numbers, so A is less than B. It said, if f is a polynomial function, so that f of A is less than f of B, then there's an interval that has every value. So it says, okay, so if we have a function, let me kind of illustrate what they're talking about here. It says if we have a function and we define A and B, and we're going to say A is negative 4, 0, right here. This is the point, negative 4. The function is equal to 0 at negative 4. And if we say B is the value of 3, and the function equals 3 at that point, so A is negative 4, and B is 3. So if we're talking about the interval from negative 4 to 3, that's the interval we're talking about. And let's say that this graph does this. It says that there is every y between a and b has a value. Because for this function, remember we draw a function, it doesn't have any gaps. It doesn't have any gaps. So it's saying between a and b, somewhere there's a 0. Or no, it's saying, well, since this is a 0 and it's a 3, somewhere between there, the function equals 2. Since when a equals -4, the function equals 0, right? And I'm going to put it this way. When a equals -4, the function equals 0. When b is 3, the function equals 3. So that means somewhere in this interval exists every value between 0 and 3. And it may be more than one place. Like, at 1, between 0 and 1, there's 2 places where it equals something. But you can find somewhere in that interval every value between 0 and 3 for that function, because it's going to exist somewhere, and maybe multiple places. But everywhere we can find because we're between 0 and 3 right here. Between 1 and 2, there's every value from 0 to 3 right there. So that's what the interval thing is just talking about. It's the intermediate value theorem. It says if a is less than b and they're not the same, like if a and b were the same number, in the interval from a to b, the function takes on every value between function a and function b. If the function at a was equal to 0, the function at b was equal to 3, so it has every value between there. So don't let that confuse you. It's just proving that, like right here, this has a 0 in the interval from -1 to 0, because when you graph it, you'll see that. And there's both a maximum and a minimum guaranteed on there. If it's a closed interval, and a and b is a closed interval, right? This graph does not go. We're saying this interval starts and stops right here. So there's guaranteed to be a maximum and a minimum value, which we see right here is a minimum and right there is a maximum. Guaranteed that somewhere between there is a minimum and a maximum. That's all that's saying. All right. You can identify test values. They're just saying how to do that. So, all right, that is, and there's more examples if you want to continue down. They give you more examples and go into more detail, but I just hit the summary of the lesson up at the top. But it'll go down. Finding zeros by factoring, by graphing, lots of different ways. All right. I'm not going to take up any more of your time. You got a lot to go over there. That was a long class. Right. Anyway, we got questions. See you this week. Friday is an A day, so you do have another day. Because Wednesday's testing day. We will not be meeting on Wednesday. But if you have questions, you can email me or come in Friday and see me, and I'll be here. So, all right, guys. If you're testing tomorrow, knock it out. Do well on that work keys. You can earn a certificate that you can show employers to show, hey, I'm a very employable person, because there's a national certificate you can get that follows you for life there. So do well tomorrow, guys, and we will see you next time.